All right, welcome. My name is Brandon Eugene, and today we are going to be learning about linear and nonlinear regression. We are going to be learning this through the visible representation of water vapor pressures, and we're going to get these measurements and calculations through the Anton equation. Here it is, where P is the vapor pressure, T is temperature, and BC and A are also just constants specific to what we are talking about. So first, let me start with, this is Google Collaboratory. This is an interface where we're able to code and import data as well, and I'll show you a lot more to do with it. But first, we're going to get our water pressures. Let me just go here real quick. It's just some data. And give me 1 second, all right? All right, so here's our water vapor pressures. Right here is our temperature, and here is our pressure measured in pascals. And what we're going to do is we're going to get the raw data. All right, let me go back to Google Collaboratory. And how we get here and how we import that data is capital W get. And then we have the raw data right here. And what we're going to do is we're just going to copy that URL and plug it right into our Google Collaboratory. Let's see if it works. And there we go. All right. And we see it right here. Okay, so what we're going to do next is we're going to import this as numpy and put into our Python as np. And now we want to load that data up, all right? So what we're going to do is we're going to type in data right here. And what I'm doing right now is I'm just trying to get our water pressure, vapor, and get all our calculations and the raw data that we just received onto our code so that we can manipulate it and graph it here on Zoom. So data equals np, it's not an equal sign, my fault. np dot load text, and our data was called water pressure. What was it called? Water vapor pressure. So I'll just rename it the same way. Water vapor pressure dot CSV. And keep that right there. And now back in here, where was it at? We're going to leave it right there, comma, delimiter. And it was separated, our values and everything was separated through commas, so we're going to continue that and follow the same suit. Shift enter. Well, we have a problem. Out of the space. Didn't need that one. Now I'm going to show you what our data looks like. Sorry, my laptop's running slow today. Let me see if I can. It's already plugged up. It is what it is. So data enter. There we go. And as I said, it's all separated by commas right there, which is why we continued ours with the separation of commas. And right here we have our temperature in the first column, and we have our pressure measured in pascals in our second column. Now, the way Google Collaboratory and Python indexes its variables and everything, it does, this is column 0, and this is column 1. So just keep that in mind, which is why whenever we go to our temperature, T equals data, we're going to put brackets, and then we're going to put semicolon, comma, 0. And then for our pressure, measured in pascals, we're going to put log capital P equals NP dot log 10. And then once again, data, and we're going to put 1 this time. And why did it do that? Why did it do that? All right, and we did that so that temperature is in this column and our pascals and pressure is in this column. Column 1 and 2, column 0 and 1, interchangeably. All right, so what we're going to do next is we're going to put in some graphs. This is my first recording from plotly dot subplots import make underscore subplots into and we're going to import plotly.io as PO. All right, so now we can make our plots. All right, that just enabled us to import plots. So I'm gonna leave it in light mode because I prefer light mode, unlike some people. All right, so in order to get this, we have to make our figure. So figure equals AKE underscore SUBP subplots. And row, we're gonna have 1 row and 1 column. Okay, we're going to make a scatter plot because right now we're not really trying to connect the dots. We're just trying to get our raw data onto a graph so we can just visually look at it and see what we have. Visually add underscore SCATTR. And now our independent variable is going to be temperature, x equals T, while our dependent variable y is going to be the log of P, our pressure. Our type of graph is going to be a scatter, so we just need our markers, no lines. And the name of this will just be our data. Did something wrong here. Let's see if I can figure it out. We're just going to keep going because I know that regardless, I need my layout to be on a fitted screen. Underscore layout. And we're going to have a height of 600 units compared to the screen. And we're going to do a width equal to 800. Now, let's see if I can figure out what I did wrong for my graph. We have figure out underscore scatter, blah, blah, blah. Markers are mode, we're using data for the name. What's going on here? There we go. Forgot my equal sign. Make underscore subplots is not defined. Make underscore subplots, our figure is that. Make. Did I spell something wrong? I usually do spell something wrong. So we have make underscore subplots is not defined. I wonder why though. I wonder why. From plotly dot subplots import make underscore subplots. Import plotly .spl .io that's PL, yeah. Alright, and what am I doing wrong here? Let me just retype this out. Import make underscore subplots, and let's just run everything all over again. Did we work out this time? There we go. See, sometimes it's not me. It's not my fault sometimes. Sometimes it's just how it's ran. All right. Now that we have our graph though, we can see that this is the data that we received. Definitely need to give this measurements on the side. But what we have here is our temperature measured in kelvins and our vapor pressure measured in pascals. And how we can test this to see if this data is accurate or not is we can figure out the boiling point of water. We know that the boiling point of water, the temperature is about 373. And if we go up here and we follow this line, we get about 10 to the fifth. 10 to the fifth is about 1 atmospheric pressure. So we know that this data is accurate since we can see that the boiling point of water falls within this data and is still in line with it. So what we are going to do now is we are going to use our sum squared error equation so that we can figure out how far away each of our data points are from our nonlinear regression model. I've already put it to the side here for you so you can look at it as we go along. On the top, we have our Anton equation, P representing pressure, A, B, and C are still our constant variables, and T is our temperature measured in kelvins. As you can see in our equation, we're finding the sum squared of each of our values. We are doing this so that we can figure out how far each of them are away from our line. But there's going to be positive and there's going to be negative. So to counteract that problem, we have squared each individual so that we can figure out the greater equivalence. So what we're going to do now is we're going to start our code, and we're actually going to put this into our code. How we do that for our sum squared, we're going to define it as SEE, and we are using variables, vector. This is our vector of parameters, sorry. And now we're going to unpack each one, A, B, and C. A, comma, B, comma, C. And that is going to equal our V, which is unpacking our vector, which helps us align with the equation. And then what we're going to do is we're going to basically put each of these numbers into our system of equations, and then it's going to pop out the numbers that we need and what we desire. So how we do that is NP sum, where the numbers are coming from. And now we're going to put that into our Anton equation. Log P minus A minus B divided by T plus C. And now how we deal with that is we do sum squared. And that is how we find our equation. So the data we have imported, and we're going to see how it deviates from our Anton equation model, giving us our sum squared deviation. Now, we are also going to minimize any error that we may have by going to Skype optimize. This is basically a way of minimizing and optimizing all of our parameters so that we have the best data possible, so that we can scrunch it and find the correct parameters. And it's already an equation built for us. We just plug it into Python and let it do its magic. So how we go from here is we hit Shift Enter, and from Skype, how do you spell optimize? Optimize, and then import our minimization. Yes, sir. Now we're going to go down here and see what we get. So we're going to minimize our standard, our sum squared error. Minimize. Did I do it? Yeah, minimize. We're just going to plug in random variables. Yeah, comma. My favorite number is 13, by the way. You didn't know. 113. All right. We're going to see what that gives us. All right, so we've done this correctly. Our array down here is x right here. And since we are finding the variables for x and just for only x, we're going to put dot x. And minus is our day, put day. It should give us the array. There is our array. All right. So once that we have this array right here, with the results from our minimization, it gives us x, which allows us to see the parameters for the model that we have currently. And what we are going to put in here is we're going to trade out the A, B, and C, and we're going to now make them our non-linear regression model constants A, B, and C. So how we do that, we're just going to simply put A underscore non-linear regression, B underscore non-linear regression, and C underscore non-linear regression. This lets us add, now we need to add a new scatter plot for our non-linear regression model using our fitted values. So let's get rid of that, shift enter, we have this now. All right, 5G, I'm gonna add a new plot in here. Underscore scatter x equals t, and y still equals a underscore and l, comma, what is our equation? It's not comma. A underscore and l minus b underscore and l divided by t plus c underscore and l. And what we're going to do next is comma. And we're not going to do a scatter plot this time. We're actually going to be using lines so that we can really get our model together. All right, and we can see our nonlinear regression line. And this is coming from the Antoine underscore nonlinear regression. So let's see how we do. What did I do wrong? Oh. Now, if we do have a poor guess, it is not going to fit the data, so be careful. Ay. Keep messing up here, y'all. Sorry, just give me 1 second. Says this is not right. I wonder if I have something misspelled. Antoine, then L is our nonlinear regression. Just give me 1 second to figure it out. Fig.add scatter. We have our x. We have our. Let me space all this out. We have our x. We have our y. A minus b divided by t plus c. Give me 1 second to figure this out, alright? Invalid syntax. Name. This is the name that we are using though. So how did I do this wrong? I want a space. It just doesn't like the fact that we added a name in the first place, it looks like. I forgot to add a comma between after lines and then separate that, so it was giving it one giant line. Shift enter. Man, thought we had it this time. I really thought we had it. Name a underscore nl is not defined. I wonder which one is not defined. So backspace out of here. Give this that space it needs. Shift enter. We're gonna get this today, y'all. I promise you that. Give me a graph. A underscore NL is not defined. A underscore NL. A underscore NL, comma B underscore NL. It says it's definitely defined. Did again. Forgot the comma. Is there a comma there? No, I don't think there's a comma there. No, there's not a comma there. Try it again. Oh, looks like I forgot. Messing up the code today. Fig dot add underscore scatter. This is the same one as before, is it not? Fig dot underscore scatter x equals t comma y log p. See, as before, we just did log p. This time we are doing our equation. Did I forget the log p? Did I forget the log p, you all? No, I don't think I forgot the log p. Minus b and l slash t plus c and l mode equals one's name and time equation. We're doing so well. We were doing so well. What did I do wrong? Let's go from the beginning. We got it. There we go. There we go. There we go. There we go. So there was something wrong with this equation up here that was invalid, which made the one below it on the scatter plot invalid as well because it did not give a value itself. Phew. I might not be the best coder, but I can code today. I'll tell you that. Man, that's crazy. All right. So now that we have this scatter plot, oh no, not a scatter. Well, now that we have this non-linear regression line, if we actually zoom in, there it is. You'll see that it really isn't touching each dot. What it's doing is it's showing how close each dot should be to each other. So let's just pan back out. All right, so what we have done so far is we have found our non-linear regression model. But there is another model that we can use to figure out our deviation for the point, and that is our linear regression model. The way we do that is, it's already above me. The math is right there. So how we start is first we take our equation and we separate our values. So we have t plus c, and we have log times log p equals a times t plus c minus b. And now we separate our t log p, so that becomes our y equals. And now we have t log p equals a times the temperature minus c times our log p plus a times c minus b, which in all essence is just our d variable. And so what we do is we put this into a matrix. So in our first column, we have our temperature measured in kelvins. Then we have our pressure measured in pascals. And then next we just have a 1 going all the way down so that our constant variable d is just multiplied by 1 so we know what it is at all times. After we have distributed the t log p amongst the Anton equation, we can now express these through design matrices, each one having their own column. So how we do that is now we have matrix X, and we're going to multiply it by our vectors V, A, C, and D, and we get our Y equals. Our first matrix is going to be, and these go down for forever or however long we need to. So we have matrix X, vector V, and our Y equals. So what we need to do is we need to find the transpose of X so that we can multiply that by X and then by our vector. Doing that will enable us to have a 3 by 3 matrix multiplied by a 3 by 1 matrix, which equals a 3 by 1 times an n by 1 because we don't know how far we're going. We still need parameters for our last y equals. And those parameters will enable to give, they will be able to give us numbers for our chart to find our linear regression model. But without that parameter, we will not be able to do this. So what we need to do is we need to find the identity matrix. We find the identity matrix by multiplying our X transpose by our normal X and then finding the inversion of that. Once we find the inversion, we can multiply that to both sides. Now on our right side, it will give us our parameters, and on our left side, it will give us our identity matrix, and then multiply that by our vector, and we have our linear regression model. Sorry, that was a mouthful, but I practiced for this one. Once we find that inversion, then we can plug all of this into our code and run it so that we will be able to experience our linear regression model and see how that relates to our data and how it compares to our nonlinear regression model. So first, what we need to do inside of our code in Python is we need to create our matrices. So our first matrix X is going to equal np.c, and the way we get that is t First column is going to be t. Oh, sorry. Second column is going to be negative log p. Yeah. And then our next column is going to be number of 1, and we're going to do np dot 1s, so they are just like t. Where are we at? And then shift enter. There we go. And now what we do next is we need to multiply the x transpose by x. And there's our equation up there. All right. So x dot t, x transpose. Multiplication of matrices is using the @ sign in Python. And shift x, shift enter. And there we have it. So our next step is going to be putting the entire equation under the x transpose identity and multiplying both sides by it. So how we do that is np, so the dollar comma, that's dot so we can multiply by the inverse. X dot t at x. Now this is this side right here. And then multiplying x dot t also. Case sensitive, do not mess up. T case sensitive times log of p. So now we have our parameters. This enabled us to find our parameters, multiplying the identity matrix, the x inverse, by our x transpose, so that we can then find our parameters for the next side, because at first all we had was a 3 by n and an n by 1. And yes, it gave us an answer, but it did not give us a region of error or a region of stability to know where we needed to reside in, if that makes sense. So what we will do next is we will actually be able to chart this up, and we also need to identify our variables. So we have our new A, our new C, and our new D. And we're going to identify those as A underscore linear regression, LR, comma C underscore LR, comma D underscore LR. And that is going to equal our N P didn't do that so right, did I? Let me just restart that, run all. A underscore LR, comma C underscore LR, comma D underscore LR, space equals, shift enter. All right, now these will be our new parameters, so we can use them as better initial guesses to see if our linear regression is better than our nonlinear regression line. All right, so A underscore LR, comma C underscore LR, comma D underscore LR. Okay. So what we're going to do next is we are going to put those variables into here and see where it gets us. What was the first one? We have a 10. 34, negative 34. And negative 2100. Yep. All right. So what we're going to do next is we are going to, sorry, that's my air conditioning. Let me figure this out real quick. So now that we see that both models work, let's add let's put these back as they were. And we're going to come down here and we're going to make a whole new plot with everything inside of it. Except this time, we're going to have t plot equals np dot li mspace np dot min t comma np dot max t 100. This allows so that if you see each of these right here they're connected dot by dot, and what we don't really want that. We want a smooth transition so we can accurately see that it's following its own line. It's not going in the path of something else. So what we're going to do here is shift enter, and it's not going to affect until we put each t-plot within the lines that we have. So we're going to put t-plot right here, t-plot right here, and we are going to re-enter our data entry. So let me just hit shift enter. So what we have, give me one more second, restart and run all so that we can get rid of our previous data, our previous line, linear regression, nonlinear regression line. And basically all we did was we gave us better parameters to start from. And now that we have better parameters, so I didn't want to get rid of it. All right, it'll be fine. It's okay. Now that we have better parameters for our nonlinear regression, which we put in there, which are these right here. But it doesn't really matter because we can put any parameters we want in there. Now we're going to put our new linear regression, and we're going to change out our variables by making this LR, BLR, and CLR. On top of that, we also need to, there we go, thank you. We need to put in our B variable, because if you see up there, B is kind of in contrast to the D. So how we do that is we put B underscore LR space equals A underscore LR times C. You gotta reverse the fact, you know what I'm saying? Times C underscore LR minus D underscore LR. And now this will give us our linear regression model. Yes, sir. Yes, sir. All right. Now, as you see, they're actually not stacked on top. And as I said before, this red line right here is our one that we initially had that was not t-plot. That is because it is going towards the next individual point. But now our linear regression line and our nonlinear regression line are in a direct flow that points are following based on a standard deviation that we have given the parameters to. Now we can't tell which one is better, but we can see that they are very close to each other. So what I'm going to zoom in. And what we have here, these will be our parameters, and we can use them as good initial guesses to see which works better, our linear regression or our nonlinear regression. Thank you for your time here. Basically today we have proved that we can graph linear and nonlinear regression lines in code through Python using Google Colaboratory. Here is my code, and here's where we start, and here's where we finish. Basically what we did was we found the water vapor pressure data, and we compared the temperature to the pressure to see where along we need our linear non-regression lines. Thank you so much.